In my talk, I will present a story which started 16 years ago and finished at least partly this year. Supernova remnant RCW86 is a shell-type supernova remnant. It's quite young. It's only several thousand years old. It's located at distance 2.3 kiloparsecs, and at this distance, its diameter is about 26 parsec. At different wavelengths, this supernova remnants appears as almost circular shell with bright protrusion in southwest. In optical wavelengths, these protrusions appear as rigid arc of radius about 1 parsec. This supernova remnant, unlike our shell-type supernova remnants, is very unusual because its expansion is very peculiar. Spectroscopic observations of southwest arc shows that blast wave expands in this direction with velocity about 100 km per second. But proper motion measurements in opposite direction for filaments shows that supernova remnant expands in this direction with velocity about 3000 km per second. In transverse directions, supernova remnant expands with velocity of 5 to 6 km per second. Such asymmetry could be understood if supernova explosion happened in between bubble produced by wind of supernova progenitor star. This idea was put forward first by Wink et al. In 1997. They proposed that stellar wind from supernova progenitor star created a low-density bubble in medium with large-scale density gradient, and due to this gradient, bubble became elongated. Bubble shown here by solid black line, and dashed line shows blast wave. So asymmetry of bubble results in that blast wave already reached in some direction wall of the bubble and significantly slowed down in these directions, but in other directions it still propagates almost freely with much higher velocities. To explain the bright optical arc in the south, people usually assume that blast wave met in this direction a dense cloudlet. And according to scenario by Wink, stellar remnant neutron star should be located in the central parts of the supernova remnant. But the interaction of the blast wave with a dense cloudlet should produce a concave dent in the shell, not protrusion. Moreover, searches for neutron star in the central parts of supernova remnants gave a null result. This was used as one of arguments to suggest that this supernova remnant was produced by type 1a supernova explosion. Before presenting my own results, I will discuss briefly structure of bubbles produced by single stars. In this sketch from classical paper by Weaver, shown bubble produced by single static massive star in homogeneous medium. Near the star, the stellar wind expands almost freely in all directions, but at some distance from star, ram pressure of wind became equal to thermal pressure of ISM, and it forms inner shock wave. At this shock wave, stellar wind is heated to very high temperature, about 1 million degrees, and this hot gas expands in all directions supersonically and produces second outer shock wave. Between two shock waves, there is contact discontinuity, which separates shocked stellar wind from shocked ISM. But such nice spherical bubbles are never produced by single massive stars, because massive stars are formed in star clusters. And these stars can find themselves in isolation in field only because if they ejected from cluster by some process, for example, by dynamical encounter with other massive stars or because of supernova explosion in binary system. So next slide shows the effect of stellar motion on the structure of bubble. Because of motion, inner shock approaches to the outer shock, and after some time, stellar winds start to interact directly with unperturbed ISM. Later on, this structure evolved in elongated structure with bow shock at the leading edge. But in reality, such structures could be much more complex because parameters of stellar wind change significantly, like mass loss rate and velocity change in the course of stellar evolution. So next slide shows possible example of bubble produced by moving massive star. The white spot on this image is a saturated image of supernova 1987A and its famous three-ring nebula in Large Magellanic Cloud. The supernova is surrounded by elongated bubble, which is attached to much more extended bubble. Wang, Dyson, and Kahn proposed that this large bubble was produced by stellar wind when progenitor star was blue supergiant star. Later on, this star evolved in red supergiant and produced smaller bubble. Several thousand years after supernova explosion, a blast wave will reach wall of this smaller bubble and will slow down in this direction. But in this direction, it will move with much higher velocity and will energize walls of this larger bubble. Probably just this situation take place in the case of supernova remnant RCWV86. In 2001, at one of conferences, I proposed that this supernova remnant is the result of supernova explosion near the edge of bubble produced by moving massive star. This scenario means that neutron star in this supernova remnant should be near the center of this optical arc. Several months after conference, Chandra observations of this supernova remnant became publicly available, and we, with Alexei Vikhlinin, found two X-ray sources just in the center of this arc. For one of the sources, source S, we found optical counterpart of magnitude 14.4 in visual, but for second source, source N, we didn't find any optical counterpart. To understand nature of this source N, we also modeled spectra of both X-ray sources and found that source S is a foreground late type active star. The spectrum of source N looks very similar to spectra of young pulsar, so we tentatively classify this source as a candidate neutron star. If it in fact neutron star, then this source N should be a very weak source of optical emission. It should not be brighter than 28 magnitude in visual. But in 2010, we observed this source with VLT and found star of 21st magnitude exactly at the position of source N. So to study the nature of this source, we obtained its photometry with 7-channel imager ground. Using this data, we estimate effective temperature of source, about 5,200 Kelvin, and excess color of 0.9 magnitude. This data indicate that we found G-type star at a distance comparable to distance to supernova remnant. But since X-ray luminosity of the source N is much higher than luminosity which we can expect for solar-type star, we came to conclusion that we deal with binary system composite of neutron star, which produce X-ray emission, and solar-type star, which is visible in optical. To check this conclusion, we obtained 4 spectra of G-star with VLT in 2015. A black line, solid line with dots shows a portion of this spectrum. And here, and this spectrum confirmed that we indeed found G-star. This figure also shows 2 model spectra. So this red dashed line shows model with solar abundances. One can see that they did not fit observations. And blue spectrum is our best fit model. From this spectrum, we derived abundances for several elements. One can see that most of them are overabundant by a factor of 2 or 3, but calcium is overabundant by a factor of 6. Such high pollution by heavy elements could be understood if this G-star was in the binary system with exploded star. And this idea was confirmed by analysis of radial velocities of this G-star. We found that they show very strong variability. During first week, velocity was almost constant. But a month later, it decreased to minus 44 kilometers per second, and then it increased a bit during the next week. This behavior shows that orbit was eccentric, and from analysis of radial velocities, we come to conclusion the most likely orbital period of this system is is less than 40 days. So here are some conclusions. So detection of strongly polluted binary G star is at the position of source N supports the idea that this source is indeed a neutron star. The large overabundance of calcium in the G star suggests that the supernova that produced supernova remnant might belong to very rare class of so-called calcium-rich supernovae. This is fast and faint transients with very strong calcium lines in various spectra. It is believed that these calcium-rich supernovae originate only from low-mass stars. But our findings hint at the possibility that some of them can originate from core collapse events also. From spectra and photometry of the G star, we found mass of the star about 0.9 solar masses. Then, assuming a standard mass of neutron star of 1.4 solar mass, we constrained mass of supernova ejecta. It should be less than 2.3 solar masses, provided that the supernova was symmetric. And mass of pre-supernova star should be less than 3.7 solar masses. This means that the initial mass of supernova progenitor was about 10-12 solar masses. But since a single star of this mass can lose only about 10% of its initial mass, we concluded that binary system lost most of its initial mass because of common envelope ejection. And we propose also that the arc in the southwest of supernova remnant is composite of material ejected during this process. The infinite short orbital period of the binary system means that this system will evolve in low mass X-ray binary after about 10 billion years, providing the first example of pre-low mass X-ray binary between a supernova remnant. And finally, I will discuss briefly what will happen with the supernova remnant itself after, say, about 10,000 years. During this time, supernova blast wave, which is plotted here, will overrun completely the dense material of optical arc and will produce second shell in addition to the already existing one. And supernova remnant will assume two-shell form. Probably just this situation takes place in the case of well-known Cygnus Loop supernova remnant. The left panel shows a Rosat X-ray image of this supernova remnant. It appears as almost complete shell with gap in the south. In 2002, Uyaniker et al. Found second shell in radio. And they also mentioned that in the center of this shell, there is candidate neutron star, X-ray source. Uyaniker et al. Proposed that these two shells represent two independent supernova remnants which interact with each other. An alternative possibility that these two shells originate from single supernova explosion of moving massive star at the edge of bubble produced by its wind. Thank you.
Thank you very much for the talk. Are there any questions or comments?
I would just ask one thing. If the neutron star itself, if the X-ray emission is, as you say, too bright to be the G star.
No, it's not accretion. It's just young star.
Yeah, exactly. I mean, unless it was in a flare state, which seems unlikely.
Yeah.
The neutron star, though, the spectral fits that I've done to it indicate that it would be odd. It would be the lowest non-thermal luminosity at the distance of RCW 86, as well as probably the lowest temperature, well, probably down with the ones that I showed in my talk that were down in the green region, so not unprecedented. So in addition to finding a really unique system, the neutron star might be pretty unique as well. I don't know if you have any comment about that.
So, please say again last part of the question.
I said, I think that in addition to finding a very unique system, you may have also found a very unique neutron star, and I didn't know if you had any comment or if you agree with that.
Okay, but I will also add to this that we observed this neutron star with Parker's telescope in 2002 and did not find any radio emission up to 25 micro-Jansky. So probably this is indeed a very unusual system. It could be affected by supernova ejecta, and we know many cases where inside supernova remnant we see X-ray source without radio emission.
Right. I was talking about the X-ray emission. It's faint.
It could be several possibilities. It could be from hotspot in the magnetic poles, or it could be non-thermal emission.
Okay.
Any other questions or comments? If not, then let's thank Vasily again.